There may come a time when you and I might want to have a single subnet to support a lot of different devices, but at the same time control the interaction on that same subnet between those devices. Well, fortunately, to help enforce that at layer 2, we can use this really cool technique called private VLANs. I'd like you to imagine in your mind a beautiful island. And on this island, a lot of people come for vacation purposes. Now, not every single person is the same on these vacations. For example, there are some people that want to go on vacation and they want to be by themselves. And so what they do, they take their boat, they arrive at the island, at the dock, and then they go to a place in the island that's isolated. Now, it's isolated from everybody else. So let's say there's 4 or 5 different people who all want to go to the island. So, for example, this is person 1 and this is person 2. They can all go to the island and they can all go to separate locations on that island where they will be isolated from everybody else. So person 1 and person 2 won't ever see each other on the island. However, they will have access to the dock so they can get on the boat and leave the island if they need to. Another group of people may want to go to the island, but they may want to go as a group. So let's call this group Group A or Community A, a community of people. So they arrive at the docks, and then they go ahead and they use this part of the island. So the cool thing about being a community is that person 1, 2, and 3 in that community can all see each other. They can hang out and they can have a good time. So they're all here in the same community, Community A. And of course, Community A has access to the docks so they can leave the island. Now, what about these isolated people over here? They don't want anybody from Community A or anybody else who's isolated to ever come in contact with them. So based on how we set this up, we would make sure that Community A would never have any contact with anybody in one of our isolated portions of the island. And the same thing holds true for Community B. We could have additional users. Wow, this yellow is yellow, isn't it? And Community B would show up at the docks. They could go down and be in an area of Community B. And Community B people could see each other, and they'd have access to the dock, but they wouldn't have access to anyone in Community A, nor would they have any access to anyone who is part of the isolated area of the island. And the same thing would hold true for a group of people who are in Community C. A separate group, they go to the dock, they go to their area on the island, they have interactions with each other, but Community C does not have interaction with Community B, Community A, or anybody else who's on the isolated portion of the island. Now the question might come up, okay Keith, what does this story right here about the island have to do with private VLANs? And the answer is, this is an example of how private VLANs operate. Let's take a look at the mechanics of this for a moment. The reason it's called private VLANs, plural, is because we're using multiple VLANs to pull this off. We're going to have a primary VLAN. In this example, it's the island itself. Let's say it's VLAN 100. That's the primary VLAN. And associated with the primary VLAN is going to be some type of an IP network address space. So let's say that primary VLAN 100 is given the IP address space of 10.40.50.0/24. That's the subnet address space associated with that primary VLAN. Then we're going to create additional subsets, if you will, of that primary VLAN, subdomains. They refer to these within private VLANs as secondary VLANs. And so what we could do is we could create something called an isolated secondary VLAN. Or we could create one or more community VLANs as secondary VLANs. So as an example, the isolated VLAN may be VLAN 200. And community A VLAN may be VLAN 300. And community B may be VLAN 400. And C might be VLAN 500. So you see when they talk about private VLANs, it's actually one primary VLAN and then one or more secondary VLANs associated with that primary. Now these secondary VLANs can be one of two types. So they can be isolated or a community VLAN. For isolated, you can have only one isolated VLAN. And that's because all you really need is one isolated VLAN. Any ports that we put into VLAN 200 in this example, because it's an isolated VLAN, those devices that we connect to any isolated port are going to be completely isolated from any other devices in the private VLAN, with the exception of this port right here, which I labeled as the dock in our analogy. Every port in private VLANs is going to have access to the dock. And why do they need access to the dock? It's so they can get in and out of this VLAN environment. And we'll take a closer look at this dock port here in just a moment. With community VLANs, you can create more than just one. If you want to have 5 or 6 or 7 different community VLANs because you have 5 or 6 different customers that all want to have interaction with other devices from that same company, you simply create a new VLAN one for each community. And then what happens is we're going to associate VLAN 300 and VLAN 400 and VLAN 500 with the primary VLAN of 100 for two basic reasons. Number one, they're also going to need access to the dock so they can get in and out of the VLAN. And devices that are in Community C, which is VLAN 500, won't have access to other devices in VLAN 400, which is Community B, because there's no cross-community communications inside private VLANs. So if a host, for example, is connected to this port right here in VLAN 500, this device could communicate with this port, that port, that port, and the dock, and that's it. This host cannot communicate with anybody in Community B, Community A, and of course no one who's connected to any isolated port of any type. So what are the port types? Well, if we have a port that's associated with a community, that would be a community port. So that's a community port for Community A, community port, community port, community port. In Community B, all the ports associated with Community B would be community ports for Community B. And the same thing for Community C. All the ports associated with Community C in VLAN 500 in our example are community ports for that community. An isolated port is any port that's associated with your isolated VLAN. So for example, here we have VLAN 200, which we've identified as being isolated. Any port on the switch that's associated with VLAN 200, the isolated VLAN, is not going to have the opportunity to communicate with anybody except for the dock, which gives that port the ability to, forward packets to its default gateway to get off the network, but it won't have access to any other ports in VLAN 200, which is the isolated VLAN. It won't have access to any other ports there, and it of course won't have access to any of the ports or devices connected to the ports in any of the other communities that are part of the private VLAN. Now, what in the world is this promiscuous port? The promiscuous port is the dock. That's the port or ports on the switch that are associated with the primary VLAN, in this case VLAN 100, and they call it the promiscuous port. I'll put a big P here because it's willing to talk with anybody. It'll be willing to talk to devices in isolated VLAN, in Community A, Community B, Community C, whatever communities you have in that private VLAN setup. The promiscuous port says, hey, I'm willing, I'll talk to anybody. And that's important because everybody on this network does need a default gateway, and it's very likely that connected to that dock is going to be our default gateway that the clients can use. So everybody who's connected to any of these ports is going to have the IP address that starts with 10.40.50. something. They'll be in that subnet. The default gateway will also be in that same subnet. And the whole purpose of the private VLANs is controlling who can talk to who inside of that subnet on that switch. And that control is implemented through the mechanism of private VLANs. And it's time for our assessment check. Take a moment, read through these questions. We'll be back to check them together in just a few moments. Good luck. All right, question number 1. Which port or ports can an isolated port communicate with? The answer is an isolated port can communicate only with a promiscuous port. That's it. And it's very likely off of that promiscuous port, we're going to have our default gateway that's sitting out there to get us off of the local network if we need to. Question number 2 is a true or false. A common subnet is shared between isolated and community VLANs. Now, the word that's a little bit misleading, I suppose, is shared, but in the big picture, the entire private VLAN scheme is sharing a single subnet. So even though ports in community and isolated VLANs cannot communicate directly with each other, they are still sharing a layer 3 common IP addressing scheme. And question number 3, private VLANs enforce traffic flow at which layer? 1, physical, 2, data link, or 3, at the network layer. And the answer to that is they are indeed private VLANs, and VLANs are enforcing layer 2 domains. And that's how a private VLAN is actually keeping the traffic separate, by doing it at layer 2 on the switch that's supporting private VLANs. So let's go ahead and configure private VLANs, and I'll walk you through the commands as we go through it together. I want to start off by just defaulting several interfaces on my switch. Interfaces gig 0/11 through 15, so they know there's nothing there beforehand. If we're running VTP version 1 or 2, we need to set the mode to transparent. If you're using VTP version 3, that does support private VLANs And in that case, we can set up a client or a server if we're using version 3. But for version 1 or 2, we need to be in VTP transparent mode. So we'll set that with the command VTP mode transparent. Next, we're going to create VLANs. Now we're going to create VLANs 500, 400, and 300. And in each one of them, we're going to simply use the command private-VLAN space community to indicate to the switch that these 3 VLANs that we're creating are going to be communities, VLAN communities inside of private VLANs. Now, although we can have multiple community VLANs, we really only need to have one isolated VLAN. So let's create that as well. We'll call it VLAN 200, and we'll use the keyword in VLAN configuration mode of private-VLAN isolated. And poof, now we have 3 community VLANs and 1 isolated VLAN. Now, of course, we also need our primary VLAN, which we decided was going to be VLAN 100. So we'll create VLAN 100 and simply use the command private-VLAN primary inside VLAN configuration mode. So let's check our work here. We have 300, 400, and 500 that we all specified as being community VLANs or sub-VLANs in our private VLAN scheme. We have our single isolated VLAN, which is VLAN 200. And then we have the primary VLAN 100, and we use the command private-VLAN for all of these, simply using the word community, the word isolated, or the word primary to indicate what type of VLAN that was going to be in our design. In our next step, we're going to tell the switch, hey, dear Mr. Switch, this primary VLAN of 100 is going to be associated with all these sub-VLANs that are participating as either secondary isolated or secondary community VLANs. And to do that, we're going to use the command private-VLAN association and then the list of all the secondary VLANs that we just created. So here's the 200, which is our isolated, right there. And 300, 400, and 500 are 3 different community VLANs that we also just created. So now the switch knows exactly which secondary VLANs are associated with the primary VLAN. Next, we're going to go into interface configuration mode for the interface that we want to be the promiscuous port, like the dock on the island that all other VLANs can access. And in interface configuration mode, we're going to specify switch port mode, private-VLAN, and the keyword promiscuous. So in interface configuration mode, now the switch knows that this port is a promiscuous port. Now, in addition, on this port, we have to specify what the primary VLAN that is going to be a promiscuous port for, and we're also going to specify the secondary VLANs, the isolated VLAN, and the other community VLANs that we created that are allowed to communicate with this port. And we're going to do that with the command switch port private-VLAN mapping the number of our primary VLAN, which is 100, and then our list of these secondary VLANs, which is 200, 300, 400, and 500. So again, let's do a quick check. We created our community VLANs, we created our isolated VLAN, we created our primary VLAN. We told the primary VLAN what the associated secondary VLANs are going to be. And now here on this interface of gig 0/11, we're specifying that it is a promiscuous port and the primary VLAN, this port, is a promiscuous port 4 is VLAN 100. And the secondary VLANs that are allowed to communicate with this port are 200, 300, 400, and 500. So it's very likely on this port gig 0/11, we are going to go ahead and place a router. And that way, any device connected in VLANs 200, 300, 400, or 500 can have access to their router, to their default gateway, to go ahead and get off of the local network. Now, just for grins, let's go ahead and add a couple of ports and place them in the isolated VLAN. So we'll go into interface configuration mode. We're using interface range for gig 0/12 through 13, those 2 ports. And we'll use the command switch port mode private-VLAN host. Now, the tricky part for the switch is it knows, because of this command we used, that they are going to be host ports in this private VLAN configuration. However, it doesn't know, the switch doesn't know yet, which private VLAN is participating in. So to fix that, we're going to use the command in interface configuration mode of switch port private-VLAN host-association, and then the VLAN number of the primary VLAN followed by the secondary VLAN that we want this port to be a part of. So in effect, this port is now a member of VLAN 200, that's our secondary VLAN, which is also an isolated VLAN. And these ports will also have access to the promiscuous ports that are in VLAN 100, which is the primary VLAN. To add a port to our community VLANs, now we have 3 of them to choose from, VLAN 300, 400, and 500. All we'd have to do is go into interface configuration mode for the port that we want to add to one of those VLANs and say switch port mode private-VLAN host, just like we did previously for the isolated VLAN, but this time, As we use the command switchport private-VLAN host-association, we'll list our primary VLAN followed by the community secondary VLAN. So the big difference here between ports 12 and 13 and port 14 is that we've linked port 14 to the secondary VLAN of 300, which is a community VLAN. So the good news is for this port, any other ports that are also part of VLAN 300, they'll be able to communicate with each other because they are in the same sub-VLAN or same subdomain or same community as each other. And just for grins, let's go ahead and throw port gig 0/15 into the other or one of the other community VLANs that we created, and that's VLAN 400. So we use the command switchport mode private-VLAN host, and then switchport private-VLAN host-association, the number of the primary VLAN, and then the secondary VLAN that we want this port to be associated with. In this case, it's VLAN 400, so we'd use this number as our secondary VLAN, which is 400. So again, other devices that are connected to other ports, which are also part of VLAN 400, would be able to communicate with each other, as well as any promiscuous ports on the primary VLAN. Also, it would be very helpful if these interfaces, these ports, were in an up state. So we'll go to interface range for them and do a no shutdown just to make sure that they are up. A really important aspect for you and I in these videos is that as we watch something, we'd also want to make sure we practice it as well and verify that it's working. So a simple command that we can use with private VLANs is show VLAN space private-VLAN, and that will show us the details for our private VLAN configuration. So here it's showing us the primary VLAN, which is 100. We have our secondary VLANs, the isolated, which is 200, and 300 through 500, which are community VLANs. It's giving us the types right here as well. And currently it only shows port gig 0/13 as participating in our private VLAN scenario. Well, that's because I don't have any devices connected to those other ports. So I'm going to take off the headset just for a moment and walk in the other room, plug in some devices so that we have link on those other ports. And then those ports which are associated with our private VLANs, they should start to show up here. Okay, so I am back. Let's use the up arrow key. Now that I have devices plugged into those ports, we'll do a show VLAN private-VLAN again. And what this command is showing us is that we have our primary VLAN, our secondary VLAN, and it's showing us the ports involved in them. So for example, gig 0/11 is in our primary VLAN. It is our promiscuous port. Gig 12 and 13 are members of the isolated VLAN, which is VLAN 200. Port 14 is part of the community VLAN, which is VLAN 300, and port 15 is participating in a different community, which is VLAN 400. And the reason it doesn't show any additional ports here associated with VLAN 500 is because we didn't configure any additional ports to be part of VLAN 500 in our private VLAN. We can also do a show interface for example, gig 0/11, which is our promiscuous port with the keyword switch port afterwards. So the actual command is right here. And that also will give us some insight regarding the role that that port is playing. So it is a promiscuous port. Administrative refers to how it's configured. Operational is referring to how it's doing. Those are identical. That's a good thing here. So the primary VLAN is VLAN 100, and the secondary VLANs are 200, 300, 400, and 500. And VLAN 200 was our isolated VLAN, so any ports in VLAN 200 wouldn't be able to see any other ports anywhere except for the promiscuous port. On the other end, VLANs 300, 400, and 500, any ports in any one of those specific VLANs respectively would be able to see other devices in that same secondary VLAN, that community VLAN that they were a part of. So if we had several devices, and they were all connected to these secondary VLANs, these subdomains, if you will, inside of our private VLAN configuration, all of them logically would be on the same IP subnet. One other thing that you and I got to chat about before we leave this nugget is some security considerations regarding the use of private VLANs. Because all these devices are on the same subnet, let's say they're in the 10.1.1.0 subnet, just as an example, and maybe the default gateway that's connected to this port, this is our promiscuous port, maybe that router has the IP address of .1. Maybe that's router 1. And here's my question. If a device here had the IP address of .25, and over here in Community C, we had a device connected to this port, and it had an IP address of .35. Even though these two ports can't communicate directly with each other, because this port's an isolated port and this port is in a different community, what would happen if the attacker or the device on this port sent a packet to 10.1.1.35, but forwarded it to the layer 2 address of the default gateway? Well, if the default gateway has a route and it's directly connected to this network, the default gateway could then route it back to that port. And then you'd have communications between this port and this port. Indirectly, because they're going through R1, but they still have the ability to communicate. So to solve that, if we're using private VLANs, we could also implement an access control list on R1 inbound on this interface. And that access control list might say something like, please deny anything from 10.1.1 if it's also going to 10.1.1. And that way R1 wouldn't be doing any hairpin turns to route traffic from the 10.1.1 network back to other devices on that same logical IP network. So that would be an important security consideration as well as we consider the use of private VLANs in our infrastructure. And my friend, for our assessment check, take a few moments, read these 3 questions. If you need more time, just hit pause during the music, and we'll be back together to review them together. Good luck. And here we go. Question number 1, when can we use a VTP server or run VTP in server mode with private VLANs? And the answer is if we're using VTP version 3. If we're using version 1 or 2, we have to set our VTP mode to transparent. Question number 2, how can private VLAN security be bypassed? And the security of a private VLAN can be bypassed if a device, for example, on an isolated port or in community B, for example, sends a packet to the layer 2 address of its default gateway. In our example, we used R1, but at layer 3, it's going to be routed back to a device on a different community VLAN. And that's referred to as a hairpin turn or hairpin routing on this interface of R1. And the third question is, how can that be prevented? And the answer is we could put an access control list, ingress or inbound, on this interface in R1 that says, please deny traffic if it's coming from this specific IP subnet and going to that same IP subnet. That way, when the device connected to this port sends a packet to R1, if it's destined for the same IP subnet, R1, based on the access control list, will deny that packet and prevent the security breach. How did you do? If you got 3 out of 3, good job, my friend. Way to go. Address resolution protocol is in use all the time in IPv4 networks, and it can be abused by an attacker who's trying to compromise our network. What I'd like to do in this nugget is chat with you about the types of compromises that can be done with ARP and what you and I can do as far as concept-wise to help protect against that. Let's begin. Can you imagine that this attacker right here really desperately wants to listen to the conversation between this PC and anyone it's talking to on the internet? Now, one way that we've already identified of eavesdropping on that traffic is to do a CAM table overflow attack, which would have the switch forward the frames to all ports so that the attacker can listen in. However, we solved that problem with port security. By limiting the number of MAC addresses that this switch would be able to learn on port 2, we've mitigated the CAM table overflow attack. However, this attacker still wants to compromise the security and confidentiality of this PC's conversations, and he wants to eavesdrop. Another method that the attacker might use is to use a technique called ARP poisoning or ARP spoofing. And the way it works is by taking advantage of the address resolution protocol. So to really appreciate an ARP spoofing or ARP poisoning attack, let's take a look at what's inside of ARP messages. In frame number 1 here in this Wireshark capture, we have an ARP request. And what I'd like to do is focus on the payload of this request. And in the payload of this ARP request, it says that the sender's IP address, the person who's making this request, their address is 10.3.0.1, and the sender's source MAC address is this one right here. You'll notice in this request, it also has the target IP address of 10.3.0.2, but it does not yet know the layer 2 address. I mean, that's the whole purpose of an ARP request, is to discover what the layer 2 address is of 10.3.0.2. Now, just for a moment, let's take a look at the layer 2 information. We have the source MAC address in the frame of the sender of the request, which should match, by the way. So A here should match A here. And the destination of the frame is a broadcast. And that's so all the devices that are sitting on the network, if we have 5 or 10 or 15 devices, the switch is going to forward the frame to all other ports in the same VLAN. And when all these other devices see that broadcast destination MAC address, they are so curious about what's inside, they will all de-encapsulate it and look at the payload here. And then as they look at this target address of 10.3.0.2, all of them are going to say, nope, not me, not me, not me, not me. They're going to basically drop it at that point, except for the one device whose IP address is 10.3.0.2. And that device gets really excited because it's about to send an ARP reply. So next, let's take a look at the ARP reply, which is in frame 2 in this Wireshark capture. And again, more training on Wireshark specifically is available in the Wireshark course here at CBT Nuggets. And I think every technician should have at least a basic understanding of Wireshark. And what I've discovered is that people who spend a little bit of extra time in Wireshark to learn it and use the basic functions of it are going to be much better network engineers and technicians because they have the skills of Wireshark. So I would encourage you, if you haven't already, put that on your list of important things to do for your career. So in this ARP reply, let's take a look at the details. This is the host at 10.3.0.2 who's reporting what his MAC address is. And I did hard code these MAC addresses to make them very easy to read. So as we look at this payload for this ARP reply message, the sender MAC address should match the Ethernet address as well if everybody's playing by the rules. Nobody's doing any kind of funny business. And if we take a look at the target MAC address, the target MAC address in the payload should match the source MAC address that was in the original request. So here, because we're sending this reply back to the MAC address with a whole bunch of ones in it, that should also match the Ethernet header at layer 2 regarding the destination for typical ARP. And then here we have the target IP address in the payload. And that target IP address is the original IP address of the requester who wanted this information. One other aspect regarding ARP is something called a gratuitous ARP. Now the word gratuity means something that isn't required. For example, if you and I went to a restaurant and we had a great meal, it's very likely that we would leave the host or the waitstaff some type of a tip or gratuity. It's not required, but it's typically done. Well, a gratuitous ARP is when somebody did not send a request for your layer 2 information, but you just pop off a reply and you offer this ARP information regarding yourself even though you weren't asked for it. That's an example of a gratuitous ARP. Another concept that we'll often hear with ARP is something called a proxy ARP. Proxy means to do something on behalf of someone or something else. So if a router is doing proxy ARP, it could be responding to ARP requests on behalf of some other device. Maybe it's doing NAT for some other device and it wants to do an ARP reply on behalf of that device. That would be an example of proxy ARP. So now if the attacker wants to compromise the confidentiality of the conversation that PC1 is having between itself and devices on the internet, it can implement an ARP poisoning or an ARP spoofing attack. And it can do this simply by sending malicious ARP messages both to the router and to the PC. On a good day, before the attacker starts this attack, here we have the router, here we have PC1, and let's say this is their MAC address column right here. The router knows that its own MAC address is MAC address A, right here, and the router also would have learned the MAC address of PC1 being MAC address C. And vice versa. The PC would know its own MAC address, and the PC would learn via ARP the MAC address A of the router. So whenever the PC or the router need to send frames back and forth to each other, they simply put the correct destination layer 2 address on the frame and send it, and the switch does the rest. So here's what the attacker does with ARP poisoning. The attacker sends a gratuitous ARP message over to the router, and it says effectively this: hey, my address is PC1 and my MAC address is B, as opposed to the real MAC address of C. And if the router believes it, he'll think that, oh, PC1, the MAC address is B. Now, simultaneously, the attacker could also send a gratuitous ARP message over to the PC and say, hey, I'm the router's IP address, and by the way, my MAC address is B. So now PC1 believes that the MAC address of the router is B. Now, from the perspective of the router and the PC, and based on their current ARP cache, which has this invalid information in it, if PC1 wants to try to send a frame of data to its default gateway, it's going to be sending it to the MAC address of the attacker, MAC address B. Now, as a courtesy, the attacker, after eavesdropping on that data, is very likely going to want to route that to the correct MAC address so that the router can forward it out to the internet. For the reply traffic that comes back, the router gets it. It thinks the MAC address for the PC is MAC address B, so it actually forwards it to the address of the attacker, and then the attacker can route that to the correct MAC address of C, after, of course, the attackers had the opportunity to eavesdrop on that traffic, and or compromise the data integrity of that data that's in motion. Now, to actually implement this type of an attack, it's pretty simple. And if you'd like to see a demonstration of the implementation of a MAC spoofing attack, I would recommend you check out the video called ARP Spoofing Man-in-the-Middle Attack. That's in the course called Penetration Testing with Linux Tools. I think you'll have a blast. And just as a word of caution, you would never want to use any of these tools in any unauthorized or illegal manners. So in the Pen Testing with Linux Tools course, it's all about how to implement those types of attacks. But in this course, our goal is to mitigate or reduce the risk of those attacks from happening. And how can we do that? One method of reducing the risk or reducing the effectiveness of this type of an attack is to use ARP Inspection. And whenever you see ARP Inspection, I'd like you to think of the ARP police, like at a roadblock. And you can have an ARP police on every single untrusted port. And so if we had the police sitting right at that port, what they're going to do with ARP Inspection is they are going to look at every single ARP message, look at that payload, and make sure it matches up. For example, if somebody is sending an ARP message saying, hey, my MAC address is this, and the switch doesn't believe that that PC or that device's real MAC address is that address, it'll just simply go ahead and drop it. And that way the attacker won't be able to send a fictitious message over to the router or over to the PC. One of our challenges is how does the ARP police, how do they know exactly what the correct MAC addresses are for a given port? They have to get that information from somewhere. Well, the method they chose to implement this is to leverage the DHCP Snooping database, sometimes called the DHCP Snooping table. So one of the key details regarding dynamic ARP inspection is that it usually is associated with DHCP Snooping, because that's where it's going to get the information it needs to determine whether or not we have valid addresses being used inside those ARP reply and ARP request messages. Now, in some environments, maybe you're not using DHCP, or maybe we're not using DHCP everywhere. For example, this router interface right here, it's connected down to port 3 on the switch. The IP address on this router is 10.123.0.1, and that is not a DHCP learned address. It is a statically configured address. So even if we had DHCP snooping turned on, the switch would never learn about the layer 3 to layer 2 mapping on that port on its own, because this interface on the router is not a DHCP client. So does that mean that you and I cannot use ARP inspection on this port because we have a static IP address out here on this interface? The answer is not necessarily. There is another method that we can also use to train the switch regarding the layer 3 to layer 2 mappings. And that technique is to use something called an Address Resolution Protocol ACL. Effectively, we have an IP address and a MAC address in a static list, a special type of access control list called an ARP access list. So what you and I could do is we could configure an access list that says, hey, the router's IP address of 10.123.0.1 maps to this MAC address, so that when ARP inspection is done on this port, port number 3, it could be successful, because even though the information is not in the DHCP snooping database, it is in our ARP access control list, so it can verify that information from the access control list, even though it's not in the snooping database. So we can mix and match. From dynamic ARP inspection, a trusted port is one where we are not going to have the police there. No ARP police on a trusted port. ARP messages can come and go all they want, and we're never going to check them. However, on an untrusted port, once dynamic ARP inspection has been enabled, any untrusted ports, for example, like this attacker right here, or this PC, any frames trying to go into the network, if they're ARP messages, whether request or replied, they're going to be inspected for accuracy. And the verification is done via the DHCP snooping database table, which has the MAC address information in it, or the ARP access control entries that we have manually created. And after the switch has looked at the payload of the ARP messages and identified that the information is correct, the switch is going to let those frames into the network. Or in the case of the attacker, if the payload information in those ARP messages doesn't match up with what the switch believes to be accurate, the switch is going to drop that frame, so the ARP message cannot do its damage that the attacker wanted it to do. And let's say every one of these ports is participating in VLAN 1, 2, 3. If we enable dynamic ARP inspection on that VLAN, every port by default will be untrusted. That's the default state. So all we really need to do, you and I, is we need to go into ports that we don't want to have dynamic ARP inspection on and simply make those ports trusted ports. So what are some good candidates for trusted ports? Well, how about this port right here? Let's say we have a trunk link that goes up to a bunch of other devices. Maybe there's 100 devices over here on the same VLAN. And maybe on this switch, we'll call it switch 1. Maybe on switch 1 we don't want to add static entries in our ARP access control list to accommodate those devices. We'll simply go ahead and call this port trusted and not inspect on that trunk port. So if we had, for example, 4 switches all connected together, and I'll put the trunk ports in blue, It's very likely that we'd make each of those trunk connections, those ports, as dynamic ARP inspection trusted ports. And I can hear some people already saying, wait, don't we want to stop an ARP request if it's not valid? The answer is yes, but we're not likely going to do it on our trunks. It's very likely we're going to stop them on all of the access ports, where the attacker is more likely connected, and we'll stop it right at the source on those access ports. So if VLAN 123 ran across all these switches, and we enabled dynamic ARP inspection for VLAN 123, all the red ports that are in VLAN 123, they would all be untrusted dynamic ARP inspection by default. And then we would go in manually and specify that we want to go ahead and trust our trunks, specifically our trunk interfaces. Now in a corner case where we have a trunk, for example, from this router coming to port 3, and we still want to do dynamic ARP inspection, maybe we do create an ARP access control list with that single IP address and its single MAC address, and we leave that port as an untrusted port so that the switch can do verification of the ARP packets that are going in and out of that port. One additional option that we can add with dynamic ARP inspection is to tell the switch, or as we like to call them, the ARP police that are working on untrusted ports, that in addition to just looking at the payload, the MAC addresses in the payload, we can also have it compare the MAC addresses in the Ethernet header and make sure they're congruent. For example, an ARP reply will have a source and destination MAC address in the actual ARP reply message, the payload, but it will also have the source and destination MAC addresses in the Ethernet header. So by adding on header validation, it's going to make sure that those are all in agreement with each other. There's also an additional option for validation to validate the IP information inside of the payload of the ARP message. One other thing I want to add is that on untrusted ports where the ARP police is currently working, there is, by default, on an ARP inspection untrusted port, there is rate limiting of 15 packets per second regarding ARP traffic. And that's to help prevent a lot of different types of attacks which are going to be using ARP quite a bit. For example, if the attacker is doing a ping sweep across the entire subnet, he's got an ARP for all those devices to learn their layer 2 addresses. And if he sends more than 15 packets per second on an untrusted port, boom, he is done. In fact, anybody who violates the 15 packets per second on an untrusted port is going to have their port put into an error disable state, which by default stays in a down state, unless we administratively go in and re-enable that port. Beep, 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 beep. We now interrupt our regularly scheduled broadcast to bring you the the assessment check. So take a moment, read through these questions, and then we'll review them together in just a few moments. Good luck. So let's take a look together. Question number 1, what does dynamic ARP inspection protect against? So we're protecting against ARP-based attacks. That's absolutely true. So that way our caches, like our ARP caches, won't be poisoned by an attacker. And we're also preventing a man-in-the-middle attack. In the event the attacker did poison a couple of ARP caches and could trick devices into sending frames to him instead of their intended destination, we're also protecting against that type of a man-in-the-middle attack on an Ethernet network. Question number 2, how does dynamic ARP inspection learn the mappings? And the answer is we can use the DHCP Snooping database, or we can make an ARP ACL that would have those mappings in it manually. And question number 3, when DAI is enabled, what is the default port state? And that is non or untrusted, as in not trusted. Now when we're tasked with preventing ARP type of attacks, we can turn to dynamic ARP inspection as one of our tools to help mitigate that risk. Thank you for joining me in this nugget. I hope this has been informative for you, and I'd like to thank you for viewing.